Welcome back, my calculus friends. So let's take the next few minutes to talk about the integral as net change multiple choice questions that gave people the most difficulty. And the ones that gave people the most difficulty were numbers 2 and 3. So I'm actually going to start with number 3 first because I feel like it makes more sense to start with number 3 first. So number 3 told us the rate at which customers arrive at a counter to be served is modeled by the function f, defined by f of t equals 12 plus 6 cosine of t over pi, when t is a number from 0 to 60. F of t is measured in customers per minute, and t is measured in minutes. So we have our function f of t equals 12 plus 6 cosine of t over 12. And remember, this function gives us the rate at which customers are arriving to the counter. It is not telling us how many customers in total have arrived at the counter. It's telling us the rate. So it's measured in customers per minute. Now remember, this harkens back to the jet tour of calc stuff that we talked about the very beginning of the school year. So this sketch looks nothing like the graph of f of t, but let's imagine it is. And if I were to think about the units of a rectangular space between f of t and the t-axis, the units for the base of this rectangle would be minutes, and the units for the height of the rectangle would be customers per minute. Now, if I were to think about calculating the area of that space, the units for that area would equal customers per minute times minutes, yielding back the total number of customers who arrived during a particular period of time. So this was a concept that you were familiar with the idea of all the way back in September. All right, so now let's tackle the actual question that they're asking. To the nearest whole number, how many customers arrive at the counter over the 60-minute period? So essentially what they're asking us to do here is find the area between f of t and the t-axis during that 60-minute period of time. So if we want to find that total number of customers, that's what we need to do. When you use your graphing calculator to evaluate that integral, and in theory you could find this antiderivative using substitution and all that good stuff, but for the sake of argument, we'll just use our graphing calculator here. You'll end up with approximately 725 customers. I hope that helps. I feel like sometimes in the context of a word problem where there's a lot to read and a lot to digest in terms of the meanings of the functions, I really think it's helpful to always go back to those basic sorts of concepts from the jet tour about the meanings of areas, about the fundamental theorem. If we integrate a rate of change, we get back the accumulated quantity. Always keep those sorts of ideas in the forefront of your mind. It's always a basic definition that we need to apply in a kind of unique or novel way. It's usually not something earth-shatteringly new. It's always going back to those basic definitions. All right, so now let's work our way back to number 2. So number 2 said the data for the acceleration of a car from 0 to 15 seconds are given in the table below. If the velocity at a time of 0 is 5 feet per second, which of the following gives the approximate velocity at a time of 15 using a trapezoidal sum? There is so much going on there, and it's hard to digest what you think you might need to do next. But I think it's important to take the information that they've given to us there and to kind of take stock of what we already know. So the first thing is to think about what's the relationship between acceleration and velocity. And there are 2 different ways to think about this. You could think about it as acceleration is the derivative of velocity, or you can think of it as the integral of acceleration is velocity, that whole fundamental theorem of Calc relationship there. So I think it's important to take stock of that first, the idea that if I were to take the derivative of the velocity, I'm going to get my acceleration. That's the first important connection to make there. The second important thing, and I think this is just something simple that you should take into consideration and write symbolically. They're telling us the velocity at a time of 0 is 5 feet per second. I think it's important to take the time to write that out symbolically. The velocity at a time of 0 is 5 feet per second. And I think it's important for us to take the time to symbolically identify what they want us to find. And they want us to find the velocity at a time of 15. Now, without even really considering the information that they've given us in the table, if I were to take the fact that the derivative of velocity is acceleration, and the fact that I know something about the velocity at 0 and I want to find out something about the velocity at 15, I can take my fundamental theorem and use that to construct an equation that relates these concepts. So if I integrate the acceleration from 0 to 15, that would equal the velocity at 15 minus the velocity at 0. That is an equation that relates the concepts that are outlined for me in this problem. So now the whole idea of using a trapezoidal sum makes so much more sense, because we can use a trapezoidal sum to approximate the definite integral from 0 to 15 of our acceleration function. So I'm going to do that. When you look at that table of values, you'll notice that between every coordinate pair given to us, the time in seconds is uniformly 3. So we go from a time of 0 to a time of 3 to a time of 6 to a time of 9 to a time of 12 to a time of 15. What that tells me is that each of the trapezoids that I am creating is going to have a uniform height rather, of 3. So my first trapezoid is going to have a height of 3, and its 2 bases are going to be 4 and 8. And then my second trapezoid is also going to have a height of 3, but it's going to have bases of 8 and 6. And my next trapezoid will also have a height of 3, but it will have bases of 6 and 9. And then 9 and 10 for my next trapezoid. And for my final trapezoid, bases of 10 and 10. Now, algebraically, if you want to make these calculations a little less cumbersome, what you can notice is that they all have a common 1/2 times 3. So I could factor that out if I want to kind of think about this a little bit more, in a more algebraically sophisticated way. So these were all the trapezoids that I wanted to add up their areas. They all have 1/2 times 3 as part of the expression for all of them. Then each of the given y coordinates shows up twice, like 8 and 8 and 6 and 6 and 9 and 9 and 10 and 10, except for the 2 on the end, because the 2 on the end are only used as the bases in the trapezoids on either end. So if you want to write this in a slightly more algebraically complex way, so this is kind of a shortcut way to manage those trapezoidal sums. If you like kind of thinking about it and setting it up this way, it's a great way to save yourself a little time, but it's absolutely not necessary. So when you do all of those calculations as an estimate, we end up as our estimate 120. So 120 is our best trapezoidal estimate for the definite integral from 0 to 15 of a of t. So we want to find the velocity at 15. We know that the velocity at 0 is 5. So now I can solve for the velocity at 15, and it's 125 feet per second. So just to recap, a couple of strategies that are going to help you on problems like these is to always take the time to kind of go into your mental interactive notebook and identify the relationships between the concepts being presented to you in the problem, and then take the time to take the given information and write it symbolically. When you take the time to put those pieces together, you're going to be able to make those necessary connections. Anyway, hope this helps. Miss you guys a lot. Keep asking questions. You're doing incredible work. Hang in there, and I hope to see you soon.